So thanks very much. Thanks to the organizers for the chance to be here, which is fantastic, and talk about some thoughts on a possible role for all these IDRs that we've been hearing about. So if you're not in, you're out, whether conformational entropy of intrinsically disordered proteins could bar intruders from biomolecular condensates. This is work with Jun Zhang, sitting over there, and her student Vladimir. So, brief outline of what I'm going to address today. There is an important question of who's in and who's out of condensates. I think we all appreciate that. And we also all appreciate that there's these intrinsically disordered regions, and there may be a connection between the two. So I'll start with a discussion of that, but also then show some simulations that June and her student have done, showing that there's a free energy barrier associated with these IDRs to intruders. Some scaling analysis of that, and then a discussion of how that interplays with the idea that there are things who are in condensates as well, how recruitment takes place in the presence of these IDRs, and then very, very briefly talk about connection to experiment. And that's something I'd love to discuss with people in the audience about what's the right way to test some of these ideas. And I will then conclude. So you've probably all seen this exact same image, so I will not spend too much time on it. But of course, there are all of these different condensates playing all of these wonderful roles in biology. But essentially, well, without exception, these roles depend on which molecules are inside the condensates, but also which molecules are outside the condensates, which are supposed to be excluded. And so that's certainly a big question for the field, particularly from the physics side, is what are the mechanisms that are controlling who's in and who's out? So an important point about these condensates is that even though we like to say things like, oh, it's like oil and water, they're not like oil and water, right? Because oil is dense inside of water. There's very, very little water inside of the oil, but in these condensates, they're really a network liquid. There's lots of space inside of these condensates. The actual volume that's filled by the scaffolds is something like 10% of the volume. It's not 90%. And so there's plenty of room inside for other things. And of course, that's important. There's lots of clients that are to come in, but that means there's also plenty of room for intruders, things that you don't want inside of your condensate. And so that has led to, this paper with this nice title, Who's In and Who's Out, Compositional Control of Biomolecular Condensates by some of our colleagues. And I think that, on balance, the who's in is reasonably straightforwardly answered, that who's in is based on recruiting of clients by some kind of specific interactions. I won't go into that too much. There's certainly a nice review, lots of papers on this, and just the idea that you have these scaffolds which somehow have binding sites. Those could be the same sites that hold the scaffolds together. They could be different sites. This could be indirect, but the idea is there's specific binding sites for clients who just have some free energy associated with binding. That's going to, on a thermodynamic sense, partition clients into these condensates. And of course, it will depend. Which sites are available will determine which clients are recruited in, and how many sites a given client can find, either based on its own valency or the valency inside, could also depend the strength of partitioning. So far, so good, but that still leaves, as I said, 90% of the volume is still available for things that are floating around and might be dangerous, kinases and so on, phosphatases, proteases, lots of things that you don't necessarily want in your condensate. So the question is, who's out? And that is, how do you exclude all of the many, many things that are floating around inside the cell from the condensates of interest? Here's just a nice schematic. Here's my condensate. It's got some nice clients inside doing some biochemistry or some signaling, but of course it's surrounded by all the other proteins and RNAs and so on inside the cell that are not supposed to be in there. How do we keep them out? So here's where I'm gonna sell you the idea that the IDRs have something to do with this. And so of course, when you think about your proteins, of course, for a long time, all the textbooks just showed something like this: folded protein. That was a protein, but it turns out that was sort of looking under the lamppost. A lot of proteins look like this, where there's folded domains and intrinsically disordered regions, and certainly some proteins look like this, where they're just intrinsically disordered. There's really no structure. And in fact, without being too systematic about it, I think, you'll let me get away with it, that most of the scaffolds we find in condensates fall on this side. There's something with some amount of intrinsically disordered regions, often quite a lot. And so you could say, oh, well, great, people know that, we've been thinking about it, and there are lots of things that these intrinsically disordered regions are doing. There could be drivers of phase separation. There could be sticky sites here. Not always, of course. There are many cases where the IDRs are inhibiting phase separation, but they could be controlling, let's say, phase separation. Certainly controlling condensate density. They're taking up space in some way. They're controlling the density, controlling how fast things can move around, if they're limited by sticking or entanglement. Certainly, if they have binding sites for clients, they could be important for the recruitment of clients. But I'm going to argue, and June and I at least will argue, that there's another potential role, and that would be excluding intruders, keeping out the things that you don't want inside. And the physics of this is extremely simple, and here it is. Here I have these IDRs, and one thing we know about IDRs is that they're disordered. And as a result, they have a lot of conformational entropy. There are a lot of different conformations that these regions could have. And the more conformational entropy something has, the lower its free energy. So that's favorable for these things to have lots of room to move around. But that means also that if you try to put something in the way of an IDR, like some intruder, you're taking away some of its conformations, you're reducing its entropy, and therefore you're creating a higher free energy as a result of that. And so there's a kind of free energy barrier, free energy cost to putting the intruder in a place where the IDR would like to be. And so the question is that significant? Is that, is the magnitude of that effect something we should care about? And to this end, there's simulations. So we could do something to start with, and this is where June and Vladimir have done some nice simulations. This is all using this LAMMPS technique, so it's coarse grain simulations. And this is basically what you've got. This is our protein, but this is a straw man. We're setting this up in order to knock it down. So this is something which has beads with stickers. The red guys stick to the blue guys. We have a certain number of these sitting inside of here. They will phase separate, but the regions in between are purely virtual. There's just a spring. It has no excluded volume. It does really nothing at all. So these implicit spacers have no entropy because they're not real. And so if you take that and you throw in not only these polymers, but some neutral particles which just have repulsive interactions, you can see that there's some decrease of the amount of the neutral particles inside because there's some excluded volume, but it's not a big deal. It's like a 2.5-fold reduction. And you think about all of the possible neutral things in the cell, just reducing that concentration by 2.5 still means you've got everything in the kitchen sink inside of your condensate. So maybe you want to do better than that. And so here's where the second model comes in, which is just take a model where you have basically the same idea. You have some stickers, they're spaced apart, but now we explicitly model the spacers in between. And the reason that these are nice tiny little beads is so that the end up with the volume occupied in this condensate and in this one are the same. It's a little hard to see that because these guys overlap, but they're really, I'll show you, they're about 7% of the volume is occupied in either case. And yet, when you look at what happens to these neutral particles, they're much more strongly excluded. And that is the only thing that's changed here, right, is that now these spacers have some conformational entropy. And therefore, when a neutral particle gets inside there, it is restricting the conformational entropy locally of those spacers, of those intrinsically disordered region, creating a free energy cost to the system. You've reduced the entropy in some way. And that is now reducing this by 14-fold, which is at least something substantial. We're really getting rid of those intruders. So that's basically the idea. We could stop now, but I still have 10 minutes, so I got to do something. So we'll say that, all right, well, this is one simulation. Can we be more general about this? What is it that's going on? Okay, this is the 7% that I wanted to emphasize. And so we can actually do more general calculations rather than doing those simulations every time we want to calculate something. First off, we can use this Widom insertion method, which is an exact result that says, well, you can think of this as some dynamical system of things moving around and reducing entropy, but everything here is really thermodynamics. This is all properties of these equilibrium systems, and there's a thermodynamic formulation in which you can calculate these free energy barriers just by trying to insert neutral particles inside of a condensate in random locations, calculating the energy of each insertion, and then taking an average of these Boltzmann factors. And that will give you an exact measurement, if you do this enough, of what that free energy barrier would be. And you can then see, in some particular case, for some particular condensate, how that free energy depends on the radius of the particle. And you get something that begins sort of linearly, but seems to then go up as maybe some power of the radius. And so you'd like to say, well, can we understand that? And the answer is, we don't need to understand it because de Gennes understood it. And once de Gennes understands something, it's understood. And so, so the idea is, forgetting about the details of the stickers and so on, just think about this as polymers disordered polymers, and the question of what is the free energy cost of inserting some test particle in here. And de Gennes will tell us that there's a scaling relations that in one regime where the particle is very small compared to the correlation length in these polymers, you get something with some power of radius. And then when the particle gets larger, you get something with another power. In this case, we're looking at an area effect. You're basically saying that the polymers don't like to get too close to the surface here because they can't penetrate inside. Now, there would also be a volume effect. That is, you're taking up some volume against the pressure of the polymers, but we're going to be considering condensates which are always living with a dense phase and a dilute phase at the same pressure. That's by mechanical equilibrium. So that pressure effect isn't actually going to determine whether the neutral particle wants to be in the dilute phase or the dense phase, because the overall pressures are the same. But these things are going to be different if you're trying to put it inside of the condensate. And so taking a lot of simulation data, actually it's this Widom insertion method for cases where this correlation length is different because you've taken the polymers and you've put them in smaller boxes or larger boxes so that they organize with different blob sizes. We've been able to fit this basically by interpolating between these two regimes. So we have a formula where the free energy has a term like this, which is dominating when the particles are very small, crosses over to this regime. And this term is important because even if you have a particle with zero radius, a point particle, then in that case, it has the true excluded volume of all of the state that the beads that are there. And so we got to have a term that's just associated with, well, what would be the free energy cost just with that 7% of the volume, even if I tried to put in a point particle, that's there. And that's all of these fits through there. So I think we really understand the physics of this.
Basically the size of a monomer in your polymer.
I would say anything that's small, this even smaller, right? It's truly a point. Like if I tell you, here's a volume, and I want to know what's the free energy of putting a particle in there, right? It's the log of the volume. If I take away part of that volume, it's the log of that reduced volume. That's all. Okay. Great. So, but what about things? We know things do go in to condensates. So the IDRs are not always winning, and so there's this balance between the free energy barrier set by the IDRs and recruitment. And so here is a simulation where we've turned on some binding between these neutral particles and those stickers, and you see as you increase the strength or the binding strength, you can go from exclusion of these neutral particles to partitioning of the neutral particles into the condensate. And of course, as I want to sort of emphasize, it's just about free energies. So in fact, we can actually look at all of this data for this partition, and we can fit it really nicely as a sum of two free energies. One from the exclusion that we just calculated, and the other from a term that just says this is the free energy associated with having a bunch of binding sites inside that you can bind to. And so you know, even though maybe the real world is, you know, there may be some more complicated coupling, at least in the simulations, it's just perfectly sum of these two free energies. So very, very simple idea. Does this apply in the real world? Always a good question. So here's a very, very short, limited comparison to experiment. These are experiments that were already done in Cliff Brangwen's group. The idea is that the partition coefficient should just be this determined by these free energy differences in the dense and dilute phases. This is just some theory to show that, well, depending on the density of the IDRs inside of the condensate, you get a size-dependent partition coefficient. And here we've tried to model some particular case where they've tried to look at how dextrin partitions either into or out of condensates, the dextrin of different radii here, and you see the small guys actually tend to go into the condensates. The larger ones are excluded, and when we actually do the estimates, the free energy barrier for the small guys is only about 2 kT. There's probably something that's attracting them, that's overcoming them. They're effectively clients in that regime. But by the time you have these 6 nanometer and 9 nanometer guys, you're talking about 20 or 30 kT of barrier. Those guys are not getting in at all, and there's really nothing measured when the partition coefficient. Okay, so we did it. We've gotten to the end of this. To some, condensates, they are full of IDRs. I think that's true. I've argued that the conformational entropy of these IDRs creates a free energy barrier, excluding unwanted particles, so that only clients, only particles that overcome that by some kind of favorable interaction with something that's in the condensate can get in. And so, you know, now the take-home message is, if you're not in, you're out. And so I want to thank Vladimir and June and our funding, and thank you very much for your attention.
One thing I'm wondering about, I mean, of course, so these condensates in cells, of course, are much more complex than their, let's say, 2,000 proteins, and they all need to evolve an IDR. You know, I mean, what I'm wondering about is there enough evolutionary pressure to evolve IDRs on all these proteins to have this effect? You know?
So I don't think that that's necessary. I think that as long as you have a high enough overall density of IDRs in your condensate, that will create this free energy barrier. So it could come from one protein that's a scaffold.
Yeah, but normally, I mean, you have really dozens of proteins, and every protein by itself is just taking up, just a fraction of the condensate, right? So you would have to evolve IDRs on many of them. That's just my...
So I think what would happen, imagine that I had, you know, one protein in the condensate that has an IDR and the other doesn't, right? That IDR is a kind of a pressure effect, so it will take over, it will push into the volume occupied by the other one, right? So I feel like you would expect, in some sense, a kind of uniform density of these IDRs inside of the condensates. That's a bit of a speculation, but I think that would be my answer to your question, that you shouldn't think about there being a domain here which is only density 7% and has no IDRs. If you did have something, the pressure of the IDRs would compress that to a higher density. So you'd actually, maybe if you have inhomogeneous situations, you'd have low density regions filled with IDRs, high density regions without. But in some ways, that would possibly overcome the concern. Yeah.
In the transition from a excluded client to a client that's in the condensate, is there an appropriate limit where this becomes like truly a thermodynamic transition once you account for the polymer entropy as you have, or do you think it's always smooth?
So in this case, I mean, this is a statement about a single particle. So there's in no way for that a thermodynamic limit or a phase transition. So it would always be a crossover. There's always going to be a continuous change in the partition coefficient with that free energy.
Hi, Ned. Great talk. I have a question about whether you can distinguish conformational entropy per se from pore size. One thing that you could potentially do is to change the persistence length of the linkers. You could do so in a way that holds the volume, the actual excluded volume, constant. And I wonder if you could distinguish between the relative contributions of those two possible entropic effects.
Yeah, I have to say, it's a bit of a hard question, because in some things, I feel like pore size is a poorly defined concept in many ways, right? Like, I don't know what the thermodynamics of pore size is, but I would say you could imagine if there were like a really fixed pore size, then you would basically run into a limit, right? You'd say basically there's very little exclusion as much smaller than the pore size, and then above the pore size, you couldn't get in at all, as opposed to this, which would be more continuous. I'm happy to chat with you more about this. I have thought about it. It's not super clear what the experiment is. Yeah.
Ned, the dextran is also a soft particle that can fluctuate around. So does that play a role? You just
I think it doesn't change things very much. It's not like that you need the hard core of the neutral particle. It is its effective kind of preferred size, and I can have, here's the dextran, and they want to avoid each other too, right? These polymers have to avoid each other. So we have somewhat the same role as having a hard sphere trying to get in. Yeah, that's my picture.
Yeah, very nice talk. And I totally buy your story for the simulation, for the in vitro case,
yeah.
But I'm a bit more skeptical about in vivo, because we all here speak about dense phases and dilute phases, but I'm not so sure where the difference between the inside of a condensate and the outside is so extreme. So there could be IDRs outside, and that would probably lower the free energy difference that you actually get. Can you comment on that?
That's totally legitimate. I think my perspective is that there's going to be more of this disordered material at high density in the condensates, but that's an interesting question about how much is in the dilute phase in the cytoplasm that is IDRs. And I will not deny that there's going to be some, and whether it's a lot or not as much is an open question. But anyway, good point.
Maybe even vaguely related. So there's all this discussion about like IDRs, like, oh, it's condensation, or the part of. So it seems to me here that if the IDR itself is part of the condensate, right, it's involved, then it's paying some entropic penalty already. It's additionally constrained. And so I wonder if you can distinguish between free IDRs within the context of an already formed network versus exclusion by further constraining the conformational entropy of something that is involved in forming the network itself. Do you see a different,
No, I think, I'm not sure I 100% understand what you're getting at, but I would say, when I said, there are some of these things that IDRs do, that one of them setting like the density of the condensate, I think that's the same effect, right? The IDR is present by mutual exclusion, trying to maintain as much conformational entropy each, are kind of repelling each other, setting the density of the condensate. So that's the same physics as this. Just now, instead of saying, this is all about the density of the condensate, it's like, that physics also is creating a barrier to new things coming in, taking up some of that volume. I'm happy to hear your question again in more detail. Yeah.
Ned, awesome talk. Two related questions. One, if the probe particle has a conformational entropy of its own, so it's not a sphere.
Yeah.
Do you think the same scaling argument works, or there's an energy scale you have to start thinking about the entropy cost that it has to pay in that environment? And maybe I'll just ask my second one too. If you put two probe particles inside this, and if you buy the entropy argument of the conformational entropy argument, can you start seeing effective interactions between two probe particles within the condensate environment?
Yeah, in the first case, I think at least at the 0th order level, I can sort of take, this is like the radius of gyration, or the preferred size of this probe particle that's not solid, but it's its own disordered, intrinsically disordered thing like a dextran, and just say, all right, I can treat that as if it was a solid particle of that radius. But you know, that's the 0th order, and then you can say, well, there's going to be some correction to that. When it goes in, it can change its conformation somewhat. But I think that 1st order, you could just say, no, it's pretty much just the preferred size of the intruder. Then the 2nd one is, do I mediate interactions? I'm not super clear on that. Like, I wouldn't expect any long-range interactions between clients by this effect. It's more like I just have a kind of region where there's a free energy cost to being inside there. Once I'm inside, I should say, that probe particle can move around. I mean, it's kind of fine. It doesn't, you know, it's just like being at an overall higher potential. Like if I'm on a plateau or in a valley, I'm moving around. I don't really know. It's only the transitions between the two where I see strong effects. So yeah, I guess that's a separate issue. But yeah, in other words, I could still diffuse around. Like just because you are on top of a free energy barrier, on top of a plateau, doesn't mean that you can't, you know, move around and explore and so on. Yeah, that's possible. Okay, I see that. You could say, yes, there's a tendency of these things rather than sort of each independently excluding. Yeah, I absolutely agree with that. There would be a tendency for these guys, get together, there's less surface area. I mean, in a sense, that's exactly what we see. We see an R squared, so it's a surface effect. So basically, there's a surface tension associated with these particles. No, now I take your point.
Great talk, Ned. Quick question about what it means to be in, because there are kind of 2 ways that we can think about it. Those that reside in the condensates versus those that can penetrate and leave quickly. There was one time they were called like clients versus tourists. So, but for the tourists, for example, are these arguments still hold? And maybe you can comment on that.
Yeah, I mean, I think that the difference between clients and tourists is simply the free energy associated with them getting over that barrier. The client, it's a free energy well, so they prefer to be there in terms of free energy than outside. The tourists, there's a free energy barrier, but once by some fluctuation they get over that barrier, then they can tour around inside the condensate. Eventually, though, if they get to they come to the edge, they may fall out. There are also things like maybe there's some extra barrier at the surface. This is really not about what happens there, so that could tend to trap the tourist a little. There's a tourist trap effect that you might consider. But yeah, that's my take. Yes.
Yeah, nice talk. So, okay, so you varied R, which is the radius of the intruder.
Yeah.
But is a longer polymer will have more entropy or more conformational entropy? So the n of the length of the IDR just comes in with the correlation length? Or
it just comes in with the correlation. So,
okay.
In this formulation, at least, in sort of the de Gennes formulation, it's really the overall density of that contour of disordered thing. It doesn't matter whether it's all one giant long polymer or a bunch of segments, as long as they're long enough to be longer, enough contour length to be bigger than blob sizes.
Okay.
Yeah.
Because what I was thinking is we've been talking about whether it's IDR structured proteins, the drive content. And so if at the limit of n goes to 0, where there's all structured proteins, would you not?
N goes to 0 is a problem, because then I don't have enough contour to form even a single blob. And then it's packing of rods or something like that, which is a different regime. Yeah.
So this is really a nice work, and it reminds me my earlier incarnation is working in crowding. So this is sort of the flip of the crowding problem, where you have a single polymer chain in the presence of a dense suspension of particles. Here you have one particle in the presence of a dense suspension of polymer chains, and but I think the concepts are the same. Now, for the last part of your talk, when you added back some binding, but in theory you can do the same by Widom insertion. So instead of treating a particle as a hard sphere, you can do a square well, for example, and then you can calculate the free energy for insertion in one shot instead of adding it as 2 separate terms.
That's a good point. We did not do it that way. The data I showed you there was from a literal simulation, but I agree with you. If we had actually just done that with these attractive points, we could have used the Widom method. June, am I right that we did that with direct simulations, or did we use the Widom method? Yeah.
Have a very slow convergence rate.
All right, very good. All right, perfect.
I just want to comment on the question about interparticle interactions, because a lot is known about inclusions in gels. Now, whether this is a gel depends on the time scale that you're talking about, but these network liquids, and I apologize for using the word hydrophobic in oil, they're really network liquids that phase separate. On some scale, they will act like gels, and they will mediate elastic type, viscoelastic, but elastic type interactions. And the interesting thing about that is that may lead, if they exist, that may lead to a further phase separation within the condensate of your inclusions. So your condensate may have little condensates of inclusions in it. And I don't know the situation for simulating that, but that might be interesting to look for.
That's a great suggestion. Thank you. One more? Okay.
When I think about what type of IDRs end up in condensates, I think about some that don't have a large excluded volume. Perhaps my intuition comes very strongly from preon-like domains and not so much from complex coacervates, but the more glycines versus serines are in them, the better they phase separate, and so you get condensates with IDRs with relatively little excluded volume. So how should I think about that?
I'm not 100%. When you say because of the different degrees of flexibility of the I'm not missing.
It simply comes out of what we have found experimentally, that they have a stronger driving force for phase separation because they like to interact with themselves better than with the solvent. Right?
Yeah. So I want to talk with you more about that, but I do feel like this is an important issue. You could even just forming the condensate, some of the IDRs will interact with themselves or something, which will reduce their entropy. That might reduce the barrier. But I need to take that offline with you. So it sounds very interesting. Thank you.